Hi all, I'm Yisheng Wang from Group 83. I chose the Monte Carlo tree search technique. I chose it because it has time-saving and future foreseeing advantages. However, it has drawbacks. From the two screenshots, we can see that when there is a significant potential sequence, the MCTS player overloads it and takes another action. That's because even the child states of road are not fully expanded in the same time. If there is more time, strategies like reducing the number of runs or limiting the distance runs can move may be able to reduce the scale of game and improve the performance. If more powerful computer is also provided, trees can be all recorded and be used in future turns. This may also be able to improve the player's performance.
Hey y'all, I'm Intaku from Group A3, and now I'm going to introduce my value iteration player. Since Inch can be modeled as a macro decision process, and Hamdouche developed an experiment that proves that search of a global optimal policy for MDP is practical using the value iteration. Meanwhile, value iteration algorithm is guaranteed to converge to the optimal value. Therefore, we decided to implement a value iteration agent. During the development, we realized that value iteration needs to look ahead at all the possible states and calculate their value iteratively, which will cost lots of time. One challenge we found is that we need to find out the largest number of states we can look ahead, and we finally decided to only set root state and possible states after two players make one pair of actions as states of MDP. If we are given more time, I think there are two improvements we can make. One is maximize the number of states we're going to look ahead, and the second is set more rational rewards for each action. For the implementation of value iteration agent, first we model the MDP. Every state of Inch can be regarded as a state of the MDP. Due to the time limit, we won't choose the root state every time we need to select an action, as well as the possible states after one pair of actions done by two players. The transition probability is equal for all transitions, which is one or number of actions that can be done by the opponent player. The discount factor is set to 0.9. Afterwards, we used value iteration to iteratively calculate the value of each state and set the max number of iterations to 10. At last, we select the action with largest Q value as the player's next action.
Hi, I'm Charlie, and I will be talking about the heuristic search strategy implementation. We used the best first search algorithm, which explored nodes by expanding the most promising nodes according to a heuristic to find a node which contains the goal state. In the model, we define each action as having a uniform cost of 1, with goal states being any state in which the agent scores. The heuristic was made through trial and error and human intuition. The heuristic is based on the immediate surroundings of each friendly ring. As shown in the example, two friendly markers on the same line with the ring in between is rewarded, whilst two friendly markers not on the same line will be penalized. The heuristic function also looks at friendly markers that form a line with the immediate friendly marker, which is also rewarded. This leads to an agent that prioritizes friendly rings being next to friendly markers, as well as line creation. As friendly rings are almost always in front of a line, it is difficult for the entire line to be stolen. However, since the heuristic does not consider the opposing player's rings and markers, the agent cannot disrupt the opposing player's lines unless it benefits its own line creation. Also, if the agent's own line is disrupted, there is varied behavior due to different prioritization and the time limit. Lastly, there are no optimality guarantees as the heuristic is not admissible, so the path to the goal state might not be an optimal path. The best first search algorithm is simple to implement, and the base algorithm is fast. However, performance and speed are both heavily dependent on the heuristic. There is no limited depth due to the time limit, and most importantly, the opponent's actions are ignored. We also attempted a minimax algorithm with alpha-beta pruning, which could simulate opponents' actions. However, this proved to be too slow to be useful. Further improvements could be made to both the heuristic function for the best first search and the evaluation function for the minimax algorithm. Here's a quick demonstration of our tournament player utilizing the heuristic search strategy. Thank you for listening.